All right, let's jump right in. Today, we're looking at something that sounds like it's straight out of science fiction. We're talking about a computer processor that wasn't designed in a lab, but was basically discovered in the laws of the universe itself.
Think about this for a second. What if everything we do with computers, pushing electrons through silicon, trying to manage all that heat, fighting off errors, what if all of that is just fundamentally backward? What if we're essentially trying to swim upstream, fighting against the natural flow of the universe?
Because that's the big idea here. Instead of fighting nature, we build a computer that follows its rules. A machine that finds the path of least resistance, because that's just what the universe does.
Now, to get how this even works, you have to start with this foundational idea, the master curvature equation. The theory behind it is pretty wild. It suggests that information isn't just some abstract thing, it's physical. The way information is arranged literally bends the fabric of reality around it, kind of like how gravity works. It's a single, beautiful rule that connects the shape of the universe to the flow of information.
So, you might be asking, why do we even need a whole new approach? Well, it's because our current tech, as amazing as it is slamming into a wall that's built out of the laws of physics. Let's break down what that wall actually is.
First up, the big one, heat. Every single electron moving through a normal computer chip creates friction. That friction generates a ton of waste heat. It's why our laptops get hot, and it's the #1 thing stopping us from making our processors even faster. They would literally just melt.
And all that heat, it's really just a symptom of a much deeper issue, resistance. And according to this theory, it's not just bad engineering, it's a fundamental property of the universe called material drag. You can think of it like the friction that reality itself creates, and the denser the material, like silicon, the higher the drag.
And then there are errors. As we make our computer parts smaller and smaller, we start hitting the weirdness of quantum mechanics. On our neat, rigid grids, electrons can just decide to tunnel through a wall and pop up where they shouldn't be. And that quantum weirdness, it causes all sorts of random, costly errors. So, if our silicon grids are the problem, what's the answer? Well, the theory gives us something incredible. The Curvature Processing Unit, or CPU². And believe me, this isn't just a new chip, it's a whole new way of thinking about computation.
Okay, here's the most important part. The CPU² isn't designed by people drawing straight lines on a blueprint. No. An AI, using that master curvature equation, figures out the absolute path of least resistance for information to flow. It's like how water carves a riverbed down a mountain. It finds the easiest way. It's designing with nature, not against it.
The first big change is the material. Forget dense 3D silicon. The CPU² uses graphene, a sheet of carbon that's only 1 atom thick. Because it's so incredibly thin and low density, it has almost no material drag. Electrons can just zip through with way less resistance, which means less heat and much, much faster speeds.
The second game changer is the layout itself. A normal CPU looks like a city grid, all straight lines and right angles. The CPU², it looks organic, almost like a leaf or a lightning strike. The paths aren't straight, they curve and flow along the most efficient routes. And this design doesn't just cut down on heat, it also naturally gets rid of those quantum tunneling errors we talked about, making the whole system way more reliable.
So what's the bottom line? The performance jump is just insane. For certain complex problems, the kind you need for heavy-duty scientific research and AI, simulations show the CPU² could be up to 10,000 times faster than what we have now. That isn't just a small step up, that's a whole new ballgame.
And it gets better. This whole new way of looking at information in geometry doesn't just fix classical computers, it might just solve the single biggest problem holding back quantum computing: decoherence.
See, a quantum computer's power comes from how ridiculously sensitive its quantum bits, or qubits, are. But that's also its greatest weakness. The tiniest little vibration, a stray bit of energy, what scientists call noise, can completely wreck a calculation. This problem, decoherence, is the Achilles heel of the entire quantum field.
So how do you fix it? With a quantum fit architecture that has 3 brilliant layers of defense. First, instead of building one giant, fragile processor, you use lots of small, stable cores in a pyramid shape. It's way more robust. Second, you surround the core with entangled particles. This is super clever. If any noise hits the system, it breaks the entanglement, which instantly tells you exactly where the error is. And finally, there's an active shield that works like a pair of noise-canceling headphones, zapping any interference before it can cause trouble.
When you put all that together, you get an absolutely massive leap in efficiency.
Right now, people think we might need thousands of physical qubits just to create one stable logical qubit. This new architecture, it gets the job done with a ratio of just 7-to-1. That is a game changer. It makes building a real, useful quantum computer actually seem possible.
And the result is a system that is just unbelievably reliable. The simulations are showing logical error rates of less than 1 in a billion. This isn't just a vague idea. It's a real engineered blueprint for a quantum computer that actually works without constantly crashing. It's a fundamental solution to decoherence.
Okay, so we've got a revolutionary new classical processor and a blueprint for a working quantum computer. What does it actually mean for the real world? What doors does this all open?
The possibilities are just staggering. We're talking about discovering new drugs with quantum-level accuracy, but on classical computers, building super-fast 6G networks that send data along the most efficient physical path, creating perfect simulations of really complex things, like how galaxies form or how the stock market behaves. And maybe the biggest one of all, this could be the hardware we finally need to build a true artificial general intelligence.
And that leaves us with one final huge thought. For all of modern history, we've built machines that work against the grain of the universe. If we're now on the verge of building machines that work with it, well, it makes you wonder. If our tools are no longer the problem, what problems are actually left that we can't solve?